Today we'll be talking about Newton's laws. Okay. Particularly today, the Newton's first law is going to take the whole day. Okay. Newton's first law. Okay, we're going to be discussing Newton's first law, and this is a law that has to do with forces and how they affect the motion or the stability or the static or kinetic nature of the dynamics of particles. Okay, so what we're going to do is I want to know what you know about Newton's laws first. Okay, now I'll clarify some misconception about Newton's laws, especially the first law. So I'm going to take the first law, give the correct statement of the first law. Okay, and after that we'll now go ahead to see the dynamics of it. So I'm going to define some terms. So I'll clarify the law, then I define those terms, and then we see how to solve problems with Newton's first law. Okay. So how do you state Newton's first law? If somebody asks you what does Newton's first law say, what would you tell the person?
Is that the law of inertia?
Good. It is called the law of inertia. Yes, Newton's first law is also known as the law of inertia. So what does the law of inertia say?
I think of the phrase, things in motion tend to stay in motion, and things at rest tend to stay at rest. And that's how
Okay. So it says that an object at rest remains in its state of rest, and an object in motion will continue uniformly in motion at a constant velocity, means constant speed and direction. Okay, but there is a missing part. Okay, and the law from here up to here is perfect. It is the missing part that has some problem that I'm going to explain today. Okay, so what you see in many texts, they'll tell you unless it is acted upon by an external force. So unless there is an external force acting on these two objects, the one at rest or the one moving at constant velocity, unless an external force acts on that object, either the one at rest or the one moving at constant velocity, that object will remain the way. So to change the static nature of the object, or the dynamic nature of the object with uniform velocity, you have to act an external force. Do you understand? But I say this statement is wrong because of this word external force. Okay? And I'm going to give you a better statement of the Newton's first law. And even if you want to state it like this, I will give you the correct terminology that best represents Newton's first law in this place. Okay, if I ask you to explain Newton's first law, come with me here. If I ask you to explain Newton's first law, you will tell me that this board eraser is going to be on this table. Okay, it's going to be on this table. Can you see the table? Okay, this board eraser is going to be on this table. It's at rest. It will continue to be on this table unless somebody moves it, right? Unless some external force acts on it, right? The same thing, you are telling me that this table is going to remain here unless somebody takes it or carries it or some force is applied to it. Is that not? Good. You are telling me in the same way, because the same law, that this wall, that this boarding is going to remain like this unless somebody comes and applies some force and push it. Is that not? But if I'm pushing this wall, for instance, I'm applying external force. But is the wall moving? Why? Why is the law not obeying that law? It says when an external force comes, the body's, the object position or object velocity will change. So why is it not working there? you will say, I have not applied enough external force. Is that not? That's what you say. I have not applied enough external force to pull this body enough to make it change its position. Is that not? But the question is, the law you stated, the Newton's first law you stated, did not tell us how large that external force is supposed to be. You did not say that the force should be large enough, that external force should be large enough to change either the static nature of the object or the dynamic nature of the object at uniform velocity. So something is missing. You just said that when an external force is acted upon the object, that object dynamics will change. And I acted an external force on the wall, and the wall did not move. So that is the first thing missing when you state Newton's first law like this. The magnitude of the external force with respect to the resistance offered by that body is missing. So you say an object will remain at rest unless an external force acts on it. I apply an external force, this object refuses to change its state of rest. Is Newton's first law wrong? No, you didn't state Newton's first law right. That is the first thing. The magnitude of the external force with respect to the resistance offered by the body. Now, let me tell you another thing wrong with this statement. Let's go back to this table. So you tell me that this table will remain at rest the way it is unless it is acted upon by an external force, right? So let's say I need a force of about, say, 50 newtons, okay, to move this table, to change the static state of this table, okay? Now, my weight is more than 50 newtons, close to like 600 newtons or more, maybe 800 newtons. You get my point? Now, if I act my weight as an external force on this system, on this table, it's supposed to change its state, is that not? According to your statement, once an external force comes, then the state of that object will change. This is what I'm going to do to this table. I'm going to climb this table. Am I not an external force? Have I changed the state of the table? Has the table moved? Is Newton's first law wrong? Something is missing. But you told me when an external force acts on the body, it changes so something is missing. So when you state Newton's first law like this, you are hiding a lot of information. You are hiding a lot of information. So when you read some other texts, they will tell you unless it is acted upon by an unbalanced force. This makes more sense. Because when you are pushing the wall, the resistance offered by the wall is still enough to balance your weak force. That is why it's in equilibrium. When I climb this table, the normal force offered by this table is still enough to withstand my weight. It is still balanced. So until I have an unbalanced force, okay, before there will be a change in state. Do you understand? Or some text would say, unless acted upon by a non-zero net force. Makes sense. So a non-zero net force is what will change the state of the object. An unbalanced force is what will change the state of the object. Not just any external force. That is the first thing you need to understand. Now, I have an object like this. I have a force of 20 Newton acting here. A force of 10 Newton acting here. What is the net force or the resultant force?
10 newtons.
Towards the east. So is this object in equilibrium? No. Because there is a non-zero net force. Is that okay? Is that okay? So this force can change the state. What if I add another 10 Newton here? What is the net force?
0.
Good. Good. Now, I want to state Newton's first law for you in a way that will bring down the concept of what it actually entails. Okay? If you ask me to state Newton's first law, I won't state it like this. At all. At all. Even if you want to put unbalanced force or non-zero net force to replace your external force. So the external force is the wrong one, and these two are the correct one that I will accept. So even if you state it with this, it's still okay, but it hides the fundamental teachings, the fundamental, the concept that Newton's first law is trying to preach. Newton's first law is preaching something very important, that if you don't understand from the statement of Newton's first law, you get lost. What Newton's first law is teaching us is the concept of equilibrium. If you ask me to state Newton's first law, I will state it like this. Newton's first law states that when the net force, or when the resultant of all the forces acting on an object is zero, then the object is in equilibrium. This is Newton's first law. When the resultant, the net, the total of all the forces acting on an object is zero, then the object is in equilibrium. That is Newton's first law. By the time we come to Newton's second law, you will know why I have chosen this statement. Because Newton's second law now tells us that when the resultant of all the forces acting on an object is not zero, then the object will accelerate. Do you understand now? Do you understand now? Do you understand? So when the resultant of all the forces acting on an object is zero, then the object is in equilibrium. That is Newton's first law. Now, what do you mean by equilibrium? That is what Newton's first law is trying to teach us. And today, we're going to look at all the details and concept of equilibrium under the action of concurrent forces, under the action of coplanar forces. We're going to go into them, see the examples, and see all the forces that work with equilibrium. Is that okay now? So, if we accept this statement as a statement of Newton's first law, so I say, what is equilibrium? What is equilibrium? Okay? Equilibrium can be defined in a number of ways. Okay? I'm going to define it about 4 to 5 ways right now. Okay? Now I want you to come here with me. What is equilibrium? So we've been able to redefine Newton's first law and understand that Newton's first law is trying to give us a clue about equilibrium. Okay? So what is equilibrium? A body is said to be in equilibrium. A body is said to be in equilibrium. One way of defining it. When the body as a whole is at rest. When the body as a whole is at rest. Like a table, or a book on a table. The book is in equilibrium. The body as a whole is at rest. This kind of equilibrium is what we call the static or limiting equilibrium. But this is just one definition of equilibrium. I can define equilibrium in another way. Another way is when the body is moving along the straight line with a constant velocity. With a constant velocity. When you move with constant velocity, you're also in equilibrium. So equilibrium does not only mean standing in one place. Standing in one place is just an example of equilibrium. You can move in equilibrium so long as you are moving with constant velocity. Do you understand? So if you say define equilibrium, I can define equilibrium like a body is at rest. I can define equilibrium as a body moving along a straight line at constant speed. I can define equilibrium in another way. I can say a body is said to be in equilibrium When the body is rotating at a constant angular velocity, the whole body is rotating at a constant angular velocity. A particle outside the center of rotation might have centripetal acceleration. We know that. But the body as a whole moving at a constant angular velocity is said to be in rotational equilibrium. Do you understand? I can define equilibrium as this. Number 4. When the body is not accelerating. When the body is not what? Accelerating. Of course. Because when you are not accelerating, it is either you are at rest or you are moving at a uniform velocity. Do you understand? So I can say a body is said to be in equilibrium when it is not accelerating. Oh yes, I'm correct. And I can also define it that a body is said to be in equilibrium, number 5, when the resultant of all the forces acting on the body equals 0, which was our definition for Newton's first law. So when you say a body is in equilibrium, what do you mean? I say a body is in equilibrium when the net force is 0. That is not a definition of equilibrium. Because when you have a 0 net force or a 0 resultant force, it is either you are at rest or you are moving at constant velocity. So you discover that depending on your deep understanding of what Newton's first law is and what equilibrium preaches, all these bodies, all these definitions fall under equilibrium, fall under Newton's first law. And for the particle moving along a straight line with constant velocity, we call this dynamic, kinetic, sliding, or translational equilibrium. So how many kinds of equilibrium do you have? 2, static and dynamic. Or you say limiting and kinetic. Or you say sliding. Or you say translational. Do you understand? Okay. Now, we have been able to kind of make standard the fact that you can move in equilibrium. And you can be in a position in equilibrium. Now, I can define the terms I want to define. Okay, let's understand some basic terms of the different internal and external forces that can act on an object. Is that okay? When we understand those forces that act on an object, then we are able to describe the equilibrium of that body. Okay? So all we're going to discuss today is equilibrium. Then, when I introduce you to Newton's second law, we now discuss acceleration. Do you understand? We now discuss acceleration. Now, I'm going to discuss equilibrium in 2 different forms. Look at this body. Look at this body. I have 20 Newton here. I have 10 Newton plus another 10 Newton. 10 Newton plus another 10 Newton. Is this body in equilibrium? It's in equilibrium, right? Because I have 10 plus 10, 20, so the net force is 0. What about this body here? 5 Newton going down here, 5 Newton going down here, and 10 Newton going up here. Is this body in equilibrium?
I think so.
Of course it's in equilibrium. Because you have 10 Newton acting down and you have 10 Newton acting up. But this kind of equilibrium is different from this kind of equilibrium. The way we treat this kind of equilibrium is different from the way we treat this kind of equilibrium. So this kind of equilibrium is what we call equilibrium under the action of concurrent forces. And this kind of equilibrium is what we call under the action of coplanar forces. So we're going to introduce you to two laws of equilibrium. The first law alone works here. Any problem of this kind, the first law will solve it. But for this kind of problem, you will need the first law, which is the law of forces, and the second law, which is the law of torque or the law of moments. Is that okay? So now we are going to focus our attention first on equilibrium under the action of concurrent forces. Is that okay? I will start defining what is a concurrent force. What are concurrent forces? What do you mean by the weight of an object, the mass of an object, the frictional force? What kind of frictional forces do we have? The normal force. What kind of normal forces do we have? The coefficient of friction. What kind of coefficient of friction do we have? I will define all these terms and I will show you diagrammatically how these terms are shown on an object that you draw what you call the free body diagram. Is that okay? Okay. Now we'll start by defining what concurrent forces are. So, definition of some terms. The terms definition is going to take just 5 to 10 minutes. I'll define those terms. And then I'll start giving you very, very simple examples and you will see how beautiful this will come out. Definition of terms. Some basic terms. Okay, number one, the first definition we're going to see is called the concurrent forces because we want to discuss equilibrium under the action of concurrent forces. So what are concurrent forces? So concurrent forces are forces whose line of action passes through a common point. Passes through a common point called the point object. So in this case, this is the point object. All the force passes through that point. That is the point object. The point object, okay? These are concurrent forces, okay? I'll see you later. Thank you. Yeah. Thank you. You're welcome.
So it's like if they share, basically they share an origin.
Yes.
And so we typically start with those because it's a lot easier to work from the same origin because it's all vectors.
Yes.
So
But that one when they spread apart, when the body is that kind of a body that is elongated, where you have the forces spread out on the body, is different. It's no longer a point object per se because there will be some turning effect, which we call the torque. Okay, concurrent forces. So they are forces that pass through a common point, like that. So I have F1, F2, F3, F4. Okay? Coplanar forces are forces that are parallel to the same plane. You can have concurrent forces that are at the same time coplanar. Like if these forces act on the board, on the plane of the board, the way I drew them, they are also coplanar. But if another force is coming from outside here, even if they pass the same point, they are no longer coplanar because they come from different planes. You understand now? You understand? But we say coplanar, for that, the coplanar means all these forces are on the same plane.
So it's essentially two-dimensional.
Exactly. So we don't have a force coming like this. It's no longer coplanar. Are we good?
Perfect.
But now we are discussing equilibrium under the action of concurrent forces. So we've seen what concurrent forces are. Okay? That's the first definition. Now the second definition. 2. I will define the mass of an object. Physicists often define this as the amount of matter. But the main physical definition is in the definition of inertia. Okay? We quantify inertia by mass. So if you understand what inertia is, which you say the tendency of a body to remain at rest or move along a straight line with a constant velocity in a constant direction, is what we call the inertia. So this is the measure of the inertia of an object. Okay? Now, what do we mean by this? Remember we told you if I have a big body and I have a small body falling down from a height, according to the experiment by Galileo Galilei, which of these bodies will hit the ground first? Ignoring air resistance.
Neither. They make it at the same time.
They make it at the same time. Do you know why? If you understand inertia and mass, you will know why. So we say force is proportional to acceleration, according to Newton's second law, which we are going to come to. It means the proportionality constant is the mass. Force is mass times what? Acceleration.
So is this why a lot of times when you see that equation, it's emphasized as like the F is big, the mass is like small, and the A is capital, to show that the F, like force and acceleration.
It's because they are vectors.
Force goes up,
acceleration goes up. They usually put like this. Because they are vectors, so sometimes they make them bold.
Okay.
Mass is the scalar. So these two are vectors. So they are. This is just a proportionality constant. But we tell you, these two bodies will get down at the same time because they have the same acceleration g. How come do they have the same acceleration g? What is acceleration from here? Acceleration is a ratio of the force to the mass. If you have a large mass, you will have a large force of gravity pulling you. If you have a small mass, you will have a small force of gravity pulling you. But at the end of the day, the ratio of your force to your mass stays the same. Do you understand now? So at the end of the day, the ratio of your force to your mass stays the same. That is why you have the same acceleration.
So how does that work with things other than gravity?
Yes, other than gravity, you cannot tell. For example, if I have an object on a table, and I have an object that is twice massive than that object, if I apply a force F to accelerate this object, if I want to give that second bigger object the same acceleration, I will apply a force 2F because it's twice massive.
Okay.
You get it now. You get it now. That is what we mean by the inertia. So it has a higher tendency to move, the smaller one, but the other one has a lesser tendency to move because it's very massive. So you need a higher force to make it change. Do you understand? That is why the mass quantifies the inertia and is measured in kilograms as the SI unit. Now let's talk about weight. Let's talk about weight. The weight of an object. So weight, let's talk about weight. Okay? Weight, let's talk about weight. Okay, I want you guys to wait so that we can talk about weight. Now, 3. What do you mean by the weight of an object? This is the force with which gravity pulls down on that object, pulls down on it. So the gravitational force can come from Earth, as well on Earth. It could be on the moon. You can have a weight on the moon. So you need to know which force gravity pulls you on the moon. Okay? And this has to do a lot with Newton's fourth law of gravity, which we're going to come and discuss later. Okay?
So the difference between like mass of an object is essentially how much matter,
Exactly.
is there.
Exactly.
And weight is
how much force will gravity exact on you as a result of that matter content. Because when we come to Newton's first law, we said that force of gravity is proportional to the product of the mass. So it depends on the mass.
Is weight? Yeah, it says this is a force with weight. So weight is a measurement of force.
Exactly, but it depends on the mass. So if you are more massive, you will have more force of gravity. That is why the ratio of your mass and acceleration is always going to be constant for gravity. G. G. Yes. How is that? So I'm introducing these forces for you to say, if I have an object here, the weight is always in a direction downward to the center of the earth. Okay? So we said the weight W is mass times acceleration due to gravity G. Always the weight of an object. So even if you're on an inclined plane, theta, your weight always goes down, irrespective of how you're oriented. By the time we come to
so it's the same equation essentially. It's the same thing as force equals mass times acceleration, except for
acceleration is a constant.
The acceleration is constant
for this case,
and we use a different term.
Exactly.
Even though weight and force in this case are interchangeable.
Exactly.
But
so weight is an example of the kind
other way around.
Yes.
You can't just throw weight or any other force equation. Okay.
You get it now, right? Mm-hmm. So it's a special force. Okay? It's a special force. This is the weight. Now let's look at what to call the normal force. Called the normal force. The normal force is also known as the normal reaction. Okay? So the normal force acting on an object, the normal force acting on an object supported by an adjacent object is the component of the supporting force which is perpendicular to the surface being supported. So remember, when I climbed the table, I stayed in equilibrium on top of the table because the table gave me a normal reaction to balance my weight. So in a diagram, if I have an object on the flat surface, your weight W equals mg is here. Your normal force I call Fn or Fr, normal reaction. Okay? Okay? They call it normal force or normal reaction. Somebody can say Nr if you like. Okay? So that force, normal force, Fn or Nr, depending on the notation you want to use, is always acting upwards on a flat surface. But how do you know the direction is corresponding to the perpendicular direction to the surface? It's always perpendicular. So on an inclined plane, your weight is always going down, but your normal force will not go up. This is not, your normal force will always be perpendicular to the surface. So your normal force on an inclined plane will be in that direction. So it's the component of the supporting force. Okay? So if I have a weight that is bigger than what the table can withstand, the table cannot give me a normal force to balance my weight. The table will break down.
So does this have to do a little bit with, is it the third law? You know,
action and reaction.
And so because there's that much force pulling down, there's an equal amount of force.
That is the beauty. You see, that is why I'm trying to see how to relate the three laws to you. Mm-hmm. If you see those three laws, the action, reaction, the law of acceleration, and the law of equilibrium, they have a very intuitive way of connecting to each other. Mm-hmm. Okay, this is exactly like Newton's third law now. For every action, there is an equal and opposite reaction.
So we call the normal force is that it's the normal force, and then you put reaction because it's that force specifically related to gravity.
Exactly.
Okay.
Exactly.
That makes more sense.
It is the reaction from the effect of gravity. So on a flat surface, it acts directly opposite gravity. On an inclined plane, it has a component. And I'm going to explain the inclined plane. Don't worry. By the time we start taking examples, we'll end this class with examples. And then you see the beauty of this equilibrium. It's so beautiful. Hey, equilibrium is beautiful and fascinating and interesting, enticing, tantalizing. Okay. All right. Are we good? Are we good? Good. So that's the normal force. Call it the normal force. The normal force. Now let's talk about friction. So what do you mean by frictional force? What do you mean by, that's number 5 now. What do you mean by frictional force or just friction? Okay? So it is a tangential force. I'll tell you what tangential means. A tangential force acting on a surface opposing the sliding of an adjacent surface over that surface.
So it says this is a tangential force.
Yes! You know we have on the surface
opposing this. Okay.
Yeah, so it is acting on the surface, and that force is opposing the sliding. So you have a surface. Usually, the surface is like rough surface in the microscopic scale, if you see it very well. So the force acting different. So it's a tangential force. It's like a tangent on those rough edges. Okay, that's what goes a tangential force. Okay, on a smooth surface, we won't have friction. Okay, so it's a tangential force acting on the surface, opposing the sliding of an adjacent surface. So there's another adjacent surface that wants to slide on this surface. So friction is going to oppose it. So it is always in the opposite direction to the direction of motion. So what that means is if I have an object on this surface, if the object is trying to move this way with a force P, pulling it, okay, the frictional force will be here, F, opposing it. And if the force P was in the left direction, the frictional force will now change to the right direction. It's always in opposite direction to the motion. It tries to reduce to oppose the motion. Okay? 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 What is a force in general? Whether frictional, normal? Okay? It's a push or pull effect. Whatever gives a push or pull effect on a body is what we call a force. They say it is the agent of motion, or the agent that changes velocity. Let's say that. It's the agent that changes velocity. Okay? Because you can have velocity at the same time you have inertia and you are constantly not accelerating. But for you to have a force, then you have to have a non-zero acceleration. There's supposed to be
say that it's the agent that changes velocity.
Yes. So when you move with a constant velocity, you don't have force acting on you, but you have what you call momentum. We are coming there. You have momentum. Some people will say that your momentum is your inertia when you're moving, actually. But when you try to slow that object down or make it speed up more, you have changed the velocity. You've changed the momentum. The change in momentum will become what we call impulse. We're going to study that later on. So when you change your velocity, you change your momentum, you change your inertia, you have introduced the force.
So how does momentum, or is that something we're going to talk about later?
Yes, it's another topic.
Okay.
But it's related.
Of course.
It's related. Because when you say F equals ma, A is V minus U over T. So F equals mv minus mu over T. Force times time is what we call impulse. mv minus mu is your change in momentum. We are going to come there. They are all related. They are all related. You see the beauty when we come there. Okay? They are all related. Now, that is the friction. Okay? So now we've been able to identify 3 forces. We could make 4. So it means if I draw an object on a surface like this, you could tell this is the weight, mg. This is the normal force, Fn. If a force P is a pulling force, I know there's a frictional force F opposing here.
So when you're drawing the picture, the normal force, you're kind of putting it from the object, but that force is being exerted at the surface.
Yes, it's the surface that gives that force, not the object itself.
So
gravity
is pulling down into the table.
Yes,
the table is.
So I will make the object green, the force, the object exact green, and then the table blue, and the force exacted by the table blue.
Okay.
Is that okay now?
Yeah.
Good. Exactly. That's a good question. It's very important to understand because by the time we start solving beautiful problems, I have beautiful problems that will make you understand this concept of Newton's laws to the extent that when you see a problem in Newton's laws, you don't need to solve the problem. You just look at the problem, you tell the answer. You look at the problem, You tell the answer. Yes, it gets that simple. And I'll show you.
Sounds good to me.
I will show you how it gets that
That's
simple.
appealing.
You will see how it gets that simple. Just what? Just be patient. Be patient. You know, you don't need to bother. All you need to do is remember that behind every answer, there is a principle of two member. Have you heard of the principle of two member? We are coming there. It's a principle from Africa. Principle of two member. I'm going to teach you that principle. And it's going to help you to solve all physics problems without actually using your calculator. You just look at the problem, you mark the answer. You look at the problem, you mark the answer. Yes. All right. Now, it is what we call tensile force. Otherwise, the magnitude is known as the tension. So if I have a string or a cord pulling on an object, okay? So I said, what is the tension on that string, okay? The tension is the magnitude of the force with which the string pulls on that object. It's called the tension, okay? Okay? And I'm going to say something very important here. You need to know. If I have an object hanging from a roof here, okay? The object has a weight, W. That weight pulls on this thing, okay? At the same time, this guy reacts with a tension T from action-reaction, okay? But this guy is also trying to pull back on this tension. So you discover there is another tension T here that tries to resist that. So this T is the reaction from W. This T is the one that pulls on the ceiling. So this is very important to understand. Because I'm going to give examples here. It's very important to understand. The T values are the same, but when I consider this body, this is what I will do. When I consider the ceiling, this is what I will have. And we are going to consider body by body, separately. I'm coming there. That's the tension. That's number 6. So now let's look at number 7.
So I'm sure that you'll explain this, but because at that particular moment no movement is happening, is that because the two T forces are they're equal?
Because
they cancel.
We will see. Just chill.
Okay.
By the time I give an example, you will see there is equilibrium. So whatever is happening here, everything here is 0. Everything net force here is 0. That is the aim. When there is static equilibrium or even dynamic equilibrium, okay? I'm coming there. Just relax. You will see. It's as easy as taking a Fanta. As easy as taking a Fanta. Have you taken a Fanta today? You should try to take some Fanta. It helps. It helps with the solving of the physics problems. Now let's look at what we call the coefficient. The coefficient of friction. Before I come in here, we have 2 kinds of frictions. Frictional force can be divided into 2. What we call the static friction and what we call the sliding dynamic or translational friction. Okay? Dynamic friction. So when an object is at rest, the friction holding it there is static friction. When an object is moving, there is still friction, but that friction is called kinetic friction or dynamic friction. Okay? When the object is now what? Moving with some V. So the static friction, S, is always greater than the kinetic friction.
Say that one more time.
Static friction is always greater than kinetic friction. Because static friction, if I have this bag here, it's being held by static friction. Okay? So for me to push it, I need a lot of force to overcome. But once I overcome it, I don't need that same amount of force to make it move. Because the friction now is lesser than when it was static.
So is it still kinetic force when something starts to slow down, or is that static?
It's kinetic.
Okay.
Whether you are slowing, so long as you are moving, it's static. But when you are at rest, about to move, that is, kinetic when you are moving. But when you are in one place about to move, that is static.
Okay.
So whether you are slowing down, whether you are accelerating, or moving at constant speed, so long as you are moving at all, it's kinetic friction. Is that okay? Mm-hmm. Good. Now, what is the coefficient of friction? So the coefficient of friction is a ratio of the frictional force over the normal force. It's a constant for a given surface. Okay? A constant for a given surface. Are we good?
Yes.
Okay. Okay.
Actually, explain that last one more time.
Yes! There's what we call coefficient of friction. The frictional force divided by the normal force is the ratio between the friction. So we have two kinds of coefficient of friction because we have two kinds of friction. The static coefficient of friction is the static friction over the normal force. And the kinetic coefficient of friction is the kinetic friction over the normal force. So it's a constant for every surface. So when I have an object on that surface, it's going to tell me how rough that surface is for the object to move. It's called the coefficient of friction. So we have coefficient of kinetic friction and we have coefficient of static friction. So if an object is at rest on a surface, I say, what is the coefficient of friction? I'm looking for the coefficient of static friction. But an object is moving on the surface. I say, what's the coefficient of friction? I'm looking for the coefficient of what? Kinetic friction. Do you understand? It's just a ratio. We're going to give examples. We're going to see the beauty of all of this. The beauty of all of this. Okay? And frictional force depends on the nature of the surface, how rough the surface is. Okay? It depends on the weight of the object actually. So the more weight you put on an object, the more the friction you're going to have. So a lighter object will have lesser friction. A more massive object will have more friction. Is that okay? That's why it depends on the normal force.
Yeah. So just because like I've heard it a couple times, but just repeat that. Just doesn't have to be long of what that equation means.
Okay, it gives a ratio of the frictional force over the normal force in the surface.
Okay.
And it is a constant because force over force cancel, it has no unit. So if I say what's the coefficient of friction between the table and the book, it's a constant for the whole book. Anywhere the book is on that table, that thing is a constant between the table and the book. Okay?
Okay.
So it tells you how rough the surface is.
And so that variable out front,
yes,
it represents that's the
coefficient of friction. And depending on the friction, it could be coefficient of static friction or coefficient of kinetic friction.
Okay.
Depending on whether you are static or you are moving.
Okay.
But it's always the ratio of the frictional force to the normal force.
Okay.
Is that okay?
Yes.
Okay. Okay. All right. Now, I'm just going to tell you one thing. And after telling you that one thing, we'll start solving beautiful problems. We'll start solving beautiful problems. Yes. Beautiful problems. You see, we've defined all these forces, all this tension, and all that. Now, I want to tell you the first law of equilibrium. The first law of equilibrium. The first law of equilibrium. The first law of equilibrium says that for an object in equilibrium, the net force in any direction must be zero. You see this simple statement? The net force along the x-axis must be zero. The net force along the y-axis must be zero. And if you are working in 3 dimensions, the net force along the z-axis must be zero. So it means upward forces and downward forces must balance each other. Sideways forces, left and right must. That is just what it says. So if another is in equilibrium, that happens. Now let's explore the beauty of this statement. I haven't understood all the kind of forces we have now. Okay, so I'm going to give examples. Example 1. Now it's about time for you to rejoice and be happy because these examples are going to enlighten you and make this whole thing look so simple. You're going to see the beauty of physics today. Hey, you're going to see the beauty of. Actually, I was taking you to the promised land. We are getting to the promised land. So this example 1. A light bulb hangs from the top of a roof in equilibrium, as shown below. So a light bulb hangs from the top of a roof. So this is the roof. I will have a light bulb hanging from the top. So it's a light bulb. So there's light coming out. Light bulb. It's really light. Okay? Now, if the mass of the bulb is 2 kilograms, it's a heavy one. Calculate the tension in the connecting cord. Simple question. You see, these are the kind of questions I told you you will see, and you don't even need to solve anything. You just mark the answer. Tell them, you guys are just joking. Is this the kind of problem you want me to solve? You are joking. Now we draw the free body diagram. We have the bulb here. The mass is 2 kilograms. So what is the weight? mg. 2 times, let's use 10, 20 newtons. So we know the tension here is going to go upward with respect to this object. Is that not? And this is the roof. And we are told it's in equilibrium. So for this to be in equilibrium, what has T got to be?
20.
Do you need to solve? Do you need, so T has to be 20 newton because T minus 20 has to be 0 along the y-axis. The net force has to be 0. So T has to be 20 newtons for this object to be in equilibrium. The forces have to balance. So if the weight going down is 20 newtons, the tension going up was, you know what? 20 newtons. For national peace. Do you understand? That is number 1. Simple. I give example 2. Now we are going. Example 2. You're going to see the beauty in this. It's so beautiful. Like I say, tantalizing. Example 2. If the system shown below is in equilibrium, find the value of T and W. So we have a system like this, okay? We are asked to find the value of T and W. So this is the system. So they said this system, maybe there's an object here. There's a string holding the object, there's a force actor, and the weight of the object is there. So we have to find the weight of the object W and the tension in the string T. The only clue we are given is we have this force 20 newtons, and we know that the system is in equilibrium. When we see such kind of problems, we first of all rejoice because they've given us a piece of cake. This is breakfast, sir, with Fanta. Okay? Now let's digest this breakfast with Fanta. Now, this is what I will do. Okay?
Is that 30 degrees?
Yes.
Okay.
So I'll draw the free body diagram here. So I have T, 20 newtons, W is going down, and this is 30 degrees. So first of all, I know there is a y-axis that has 60 degrees here. Is that not? So the first thing to do is to resolve this T. Remember when you have a force in between axes, you get a component. So I'm going to have T cosine 60 degrees here, and I'm going to have T sine 60 degrees here. Or T cos 30, anyone you like. So this is the same thing as T cosine 30 degrees, and this is the same thing as T sine 30 degrees. So anyone you like. So what I know, this diagram reduces to this diagram because of the effective nature of my forces. So T cosine 60 degrees is here, W is here, T sine 60 degrees is here, and 20 newton is here. Problem is solved because there's equilibrium. So the left force must balance the right force. So T sine 60 degrees is 20. From here I get T. I put it here, T cos 60 degrees is W, and the problem is solved. So, if this system is in equilibrium along the x-axis tells us that these two forces must balance. So this minus that must be 0. So this must be equal to that. So from here, the only thing I don't know here is t. 0.866 times t is 20. So what is t? Is 20 over 0.866. Okay, which is 40 over root 3 meters. Now, I put that here, cosine 60, I get W. So I've gotten T and W. Like I said, you don't need to, by looking at it, you already know. See, cosine 60 is this. You just mark your answer. Because you've understood what equilibrium is truly is. You've understood what equilibrium truly is. Now, let's go to even the simplest case. This is how complicated. This thing you think is simple is complicated. Let's go to the one that you think is complicated and it's actually simple. Example 3. A box of mass 5 kilogram is pulled along the horizontal floor by, let me say 10 kilograms, by a horizontal force of 50 newtons at constant speed. Calculate 1. The frictional force. 2. The normal force. The normal force. 3. The value of the coefficient of kinetic friction. The value of the coefficient of kinetic friction mu K between the box and the floor. So next time I'm just going to say calculate mu K. You know what it means, okay? The coefficient of kinetic friction between the box and the floor. So this is the problem. This is the problem.
So
yes.
If it's moving at the same speed, then
equilibrium.
Yeah.
That is the clue you're looking for.
So if the horizontal force is 50 newtons, then the frictional force is negative 50 newtons.
You don't even need to put negative. Once you've called it friction, you've already put it there.
It's indicated that it's
50. You get it? Now you're understanding what is going on.
And you would use 10 kilograms times gravity.
10, 100 newtons to get the normal force, which is still in it. You are a beautiful, handsome boy.
And then you use that to calculate.
I like you, Patrick. This Patrick guy is like. So you see the problem now? A force pulling at 50 newtons, 100 newtons. Is that not? Sorry, 50 newtons.
Or 50 newtons.
And the weight is mg. I take g to be 10. 55 times 10. So the weight is 50 newtons. Frictional force is going this way. Normal force is going upward. And the system is moving at constant speed. So constant speed means equilibrium. So there is no difference between this system and this system. They are both the same. So what is friction? Friction must balance, so friction is also 50. What is normal force? Normal force must balance whatever is down. Normal force is also, or 10 kilograms, sorry. So this 100. Normal force is 100.
So it's...
So you've gotten the first and second answer. So what is the coefficient of friction? Mu K is frictional force over normal force. 50 over 100. 0.5. So you see, you don't even need to draw. Just by looking at the problem, you've known you are. That is the promised land I'm taking you to.
What is the coefficient you, like, we know how to get it, but why is it important?
Yes, the more the coefficient of friction you have, okay, it tells you, you can't get a coefficient of friction more than 1. Okay, it goes from 0 to 1. So if you have coefficient of 0, it means there's no friction. So it means the surface is smooth.
Okay. Okay.
You understand? So the rougher your surface, the more your coefficient of friction. So when you have a 0 friction, you have a 0 coefficient of friction, so it's smooth surface.
Okay.
Is that okay? So when you have a smooth surface, they won't ask you to calculate friction. Negligible, they won't ask you to calculate. So once you have a smooth surface, a force acting on that surface will produce acceleration because there's no friction to even reduce the motion. Is that okay? We are coming there.
Yeah.
We are coming there. Good. Is this getting? Are you coming with me to the land of Canaan, the promised land? Okay. Yes, sir. Yes, sir. Now, I'm going to make the problem a little bit complicated. The same problem, but a little bit complicated. So we have the same box, the same problem, but this time around, the force pulling the box is inclined at some angle, say 60 degrees. And the force is, say we'll have a force of, let's say 60 Newton, okay? Okay, 60 Newton. So I'm asked, is still 100 Newton weight? So I'm asked to get the same thing, frictional force, normal force, and, coefficient of friction. The same. But the force is no longer horizontal.
So you just have to calculate the horizontal.
Exactly. Now, let's get the frictional force first. The frictional force will be the horizontal component, which is 60 cos 60. That'll give us 30 meters, because there's no other horizontal force. So now let's calculate the normal force. The normal force will not be equal to the weight now, because we have another force coming here from the vertical component, 60 sine 60. So I have two forces up now, balancing the weight down. So I will say normal force plus 60 sine 60, those are the two forces going up, must balance 100 Newton going down. Then from here I can get the normal force. Do you understand? Then whatever I get from the normal force here divided by the frictional force, if I divide that frictional force divided by that, I get the coefficient of friction. Or they might want to deceive you and tell you somebody is pushing on this box with the same 60 Newton force, but this time around he's pushing, he's not pulling, he's pushing. Be careful. So your frictional force now will be going this way because it's pushing. So the component of X is going that way, it's pushing. So your frictional force is going that way now. Are you seeing now? So these are the little things you know. You are pushing at the same angle. So your frictional force will still be 60 cos 60 in that direction. Okay? The other direction. What will be your normal force? Your normal force is going up. You have your weight, 100 Newton here. When you get
so now it's subtraction.
Exactly, because the Y component is going down.
So
it's going to be normal force equals 100 plus 60 sine 60. Because these two forces are now downward forces.
You just have to remember that they're vectors.
Exactly, and put into consideration the direction. Do you understand what's going on here? Good, good, good. I like it. I like it that you understand what's going on here. All right, all right. Now, let's look at this simple example before I take you to the inclined plane. Okay? That's example 3 with different kind of changes, okay, that could happen, okay? Now let's look at another example 4, okay? So a body pulls another body about a frictionless pulley. So I have a 10 Newton object here, and I have a 20 Newton object here, okay? And this system is moving at constant speed, v. And I ask you to find the tension in this rope, the frictional force, and the normal force, and the coefficient of friction. This is the weight, 20 Newton. The pulley is frictionless. Okay? So this is where we're going to see Newton's third law collaborating with it.
Is that 10 newtons on that?
Yes.
Okay.
10 Newton pulling down, 20 Newton following at constant speed. At constant speed, that's what gives us the idea. At constant speed. So what happens at constant speed? So we know there is a weight here, mg, 10 newtons. There is a tension here. So if the system is moving at constant speed, we go body by body. We don't consider everything. We consider this first body first. So what will be T here? T will be 10 newtons. Because this body is in equilibrium. That T will pass through here. The direction of T will change. T will now be pulling this guy. T, because nothing happened to it in the frictionless pulley, it will go the same value as T, come here and pull this guy. This system turns to this system we just did. So this guy doesn't have friction because it's not touching this surface. The only guy that has friction is this guy. So what is the friction there? It's equal to T, which is 10 newtons. Because it's balancing this guy to be in equilibrium. Then you get your normal force as the weight of this guy, 20 newtons. And you can get your coefficient of friction from there.
So equilibrium equations, at least what we're doing, are really, you just have everything cancels out. So you just have to make
We need zero. We don't need any forces active. We need zero forces in every direction. Do you understand?
Yeah.
All these problems I've solved. By the time I introduce the Newton's second law with acceleration, you will see we are going to solve all those problems in a different way. The net force is no longer zero. It's now going to give us MA. Okay, and we're going to see how the examples will change. Okay, and they are very simple. They're very, very simple. All right. Now, let's look at the inclined plane. I want you to understand the inclined plane. I'll explain it today. Okay. When I have an object on an inclined plane, let me call this theta. There's an object here. Okay. The weight always acts down, W, mg. Okay. If you are pulling the object up with a force F, or I call P, there will be a friction force, small f, opposing you down there. Okay. And the normal force is always perpendicular to the surface. Fm.
So, okay, we're good. Sorry.
It's okay.
It clicked.
I'm coming. I want to explain something. Now, inclined plane. I want you to take a look at this chair. Let's take this chair as an inclined plane. You see that? Can you see this chair as an inclined plane? I put this marker on this inclined plane. I said, marker, please stay here and wait for me. I didn't push it. I just dropped it there. I said, marker, stay here and wait for me. What happens?
It doesn't listen.
It rolls down. Why? Why does the marker roll down by itself?
Is it because of rather than the normal force and gravity canceling, like they did before, holding in place because of the angle it's created, as well as it's no longer in equilibrium, obviously, and because of the frictional force and the normal force.
A lot of reasons, but let me tell you the basic idea. The basic idea is, just like you said, there's an angle. This weight in an inclined plane, we take this as our y-axis, and the plane parallel to the incline as our x-axis. So you discover that if I draw my y-axis down on my x-axis like that, the weight is now acting between the x and y-axis at the same angle, theta of the plane to the y-axis. So the weight now has two components now. A component along the y and a component along the x. So the component along the y is mg cosine theta, and the component along the y is the x is mg sin theta. So it is this component along the x, mg sin theta, that always tries to bring every object down. So unless you have friction that is enough to hold mg sin theta, any object you put on an inclined plane will always go down. So if an object is sitting on an inclined plane not going down, it means the mg sin theta that tries to bring that object down is balanced by frictional force holding it up. Do you understand? Okay. Okay. So if I have a force P, okay, trying to pull this object up at constant speed. So that force P will first of all balance mg sin theta, at the same time balance the frictional force. Do you understand? Because the frictional force will also be going down. So the key is always know for an inclined plane there is this imaginary force of mg sin theta and mg cosine theta. So if I have an object on an inclined plane, static on an inclined plane, not moving, mg sin theta is here. What is the frictional force? Also mg sin theta, okay? The normal force is going here. This is your mg, this is your theta. So what is the value of this line? Mg cosine theta, right? So what is your normal force? Mg cosine theta. So what is your mu? It's frictional force over normal force. Frictional force is mg sine theta for an object just sitting on an inclined plane, not moving, over mg cosine theta. I'll give you sine theta over cos theta, which is what? Tan theta. So sometimes they will tell you an object is sitting on an incline of 30 degrees.
So you just have to take the tangent of
What is the coefficient of friction? Just the tangent will give you. So they won't give you any other thing. And you'll be like, how do I do this? So since it's sitting on an inclined plane, you already know that the frictional force is mg sine theta, the normal force is mg cosine theta, and the ratio will give you tan theta. Do you understand? Do you understand? We are getting there. We are getting there. Okay. We are getting there. We are getting there. Okay? Now, I'm going to give you the same problem I gave before. An inclined plane. But this time around, the inclined plane has this frictionless pulley. So we have the 10 Newton here. And we have the 20 Newton here. And this guy is pulling that guy again. Okay? And I say, what is the frictional force? Okay? So we know the tension here will also be 10 Newton. To balance this weight, 10 Newton. And the tension here, 10 Newton will come here. Frictional force is going this way because the object is going there. But don't forget, we also have mg sine theta. That is the trick now. Okay? Don't forget that aside the frictional force, we also have mg sine theta going down. So what will be 10 Newton? 10 Newton will be equal to frictional force plus what? Mg sine theta. Are you getting it?
And it's saying it's in equilibrium.
Yes.
Okay, assuming. Okay.
Let me make this 15 Newtons. It's easy. Okay. Now, what will be the frictional force? Mg is 15 Newtons. Sine, let's say theta is 30 degrees, okay? Sine 30 degrees. 15 sine theta will give us 7.5. So what is frictional force? 10 minus 7.5. That'll give us 2.5 Newtons. So always remember this mg sine theta force. Do you understand?
Mm-hmm.
And you can have acceleration on an inclined plane. Okay, the whole system will be the same, but the equilibrium will turn into an acceleration MA. Okay, we're going to see those as we go along. Okay, this is just introduction to inclined planes. We're going to do more problems on inclined plane. Just always understand that there is an imaginary empty center that tends to always bring an object down, and in every of your problem, include it there before you solve anything. Okay, okay. Now I'm going to start introducing you to equilibrium under the action of coplanar forces. Equilibrium under the action of So we've seen how concurrent forces work in their different varieties and forms, okay? Now we're going to look into equilibrium under the action of coplanar forces. And we said for this case of coplanar forces, we are going to need two laws now. The first law of equilibrium, which we stated, and another law we call the second law of equilibrium, which is the law of moment, or the law of torques, okay? So what do you mean, first of all, by moment of a force? Okay, that's the first thing we're going to define. And even before then, before I define the moment and equilibrium under the action of coplanar, let me explain two things to you briefly. Okay? There is something called the triangle law of equilibrium. The triangle law of equilibrium states that if three forces are in equilibrium, they can all be represented by the sides of a triangle taken in order, in magnitude and direction. This is a very simple way of solving three-force problem, okay? So I will introduce you to the triangle law, Okay, the triangle law of forces, or called the triangular law of forces. It's just for forces in equilibrium. Okay, so what he's saying is, for example, let's take a look at this. I have a picture hanging, okay, a picture hanging like this. So the weight of this picture is, say, 20 newtons. It's hanging on the. I say, what is the tension in this string? T. Okay? Or maybe let's say they even have different angles. Let's say this is 70 degrees and this is, say, 60 degrees. So I have T1 and T2. So I said find T1 and T2, giving this weight alone. So this is equilibrium, right? Okay? So usually there are different ways to do this. Okay? One way to do it is to draw them as concurrent forces, like we did. The weight going down, okay? You draw your x and y axis like this. So this guy can translate to this point, it's a free vector, okay? So you know this angle 60 degrees, so this is also 60 degrees here, okay? So you draw it like this. You draw the forces like this, x and y axis. This guy going here, and this guy going here. You see that now? So this is T2, and this is T1. So T1, 70 degrees, T2, 60 degrees. And the weight, mg, 20 newtons. You see, I've represented this whole diagram as a point force. Then I can say T cos 60 equals T1 cos 70. And then T1 sin 70 plus T2 sin 60 will give me 20. You see that now? That's a T1 sin 70 plus T2 sin 60 will give me 20 newtons. Those are the Y forces. They will balance. And the X forces, T1 cos 70, okay, plus T2, no, sorry, minus, because it's to be in the other direction. Minus T2 cos 60 equals 0. So it means...
Would it be minus, or would it just turn out minus when you calculate the equation?
No, it will be minus because you are looking at it. It will turn out minus when you are using this angle. So if I want to use this angle to the horizontal, instead of cos, I say cos 120. then it would be a minus will come. Yes, a minus. It would fix it. It will fix it. Yeah. So it depends on the angle you are using. Okay, that's why we had to elaborate that in vectors. You have to understand the angle you are using. So because I already understand it's to the left, I put the minus myself. But if you don't want to know whether it's to the left, then you use this angle towards the positive. Then the minus will appear by itself. Okay. So I said T1 cos 70 degrees equals T2 cos 60 degrees. So what is T1? Is T2 cos 60, which is 0.5 T2 over cos 70 degrees. I now put this in this equation for T1. I solve for T2. And then put T2 back here, I get T1. So this is one way of doing it. Another way of doing it is the triangle law of forces, because we have three forces in equilibrium. So let me show you how simple that is. So triangle law of forces tells you if these three forces are in equilibrium, I will draw a triangle that looks like this, like that. You see that? Like this, like that.
It's just
and straight down.
It's
a triangle. So this is your 20 Newton, your mg. This is your T1 at 70 degrees. So this will be 20 degrees, okay? This is your T2 at 60 degrees. So 60 degrees here, right? So this is 20, this is 60, this is 70, this will be 70, right? You see that now? So this will be 70 plus 60, 130 degrees. So this is your T2. And then you cannot solve for T1 or T2. So you know the angles already, so you can use sine law. 130, 150, so here will also be 30 degrees to make 180. Okay? So you're done. So you have a triangle, let me make it bigger. This is 130 degrees, this is 30 degrees, this is 20 degrees. So everything is 180. This is 20, this is T2, and this is T1. Okay? So it says sine 20 degrees over T2 equals sine 130 degrees over 20 using sine rule. From there you just get your T2. Okay? Then sine, this is something as sine 30 degrees over T1. So equate this with this, you get T2. Equate this with that, you get T1. Just by putting them in the triangle because they're in equilibrium. Now, it's very important for you to know here the difference between resultant force and what we call equilibrium force. Okay? So we said equilibrium force. We said the resultant force is a single force, okay, which acting alone will have the same effect as two or more forces combined. The equilibrium force is that single force that will balance all other forces acting together. So the equilibrium force is equal in magnitude to the resultant force, but opposite in direction. What do I mean? If I have two forces going to the east, 15 newtons and 20 newtons, 10 newtons, what is the resultant force? 25 newton east, is that not? What is the equilibrium force? It means which force will keep them in equilibrium? It will be the same magnitude, but opposite direction. Do you understand now? Do you understand now? So if I give you two forces like this, that is why, let's look at this diagram. If I have T1 going like this, and T2 going like that, what is the resultant? We start from here, we draw an arrow to the head there, is that not? But why do we say this one's in equilibrium? Look at the arrow. It's coming down because it's cancelling the net of these two that are supposed to go up. Are you seeing now? So this is the direction of the resultant. So what will be the direction of the equilibrium? It will be the same line, but what?
So essentially, in this other picture,
yeah,
the resultant could almost be like the normal force, or is that what it's called again?
Equilibrium. What are you talking about?
But meaning, because that force is gravity.
Yes.
So meaning, in this particular situation,
yeah, it will look like a normal force.
It would be a normal force.
Yes.
Okay.
I get what you mean.
In this specific example.
That will be the resultant force. But the equilibrium force, we have to cancel that to bring it here. Okay. You get that? So the difference. So if I give you two forces, I say there is a force here 10 newtons, another force here 10 newtons, acting at an angle of let's say 120 degrees. Okay? I say find the equilibrium force. All you need to do is find the resultant force using your parallelogram law of whatever. After getting the resultant, you see the resultant will give you 10 newton this way, 60 degrees, because they are equal, to be equally shared. So the resultant is 10 newton in between, the equilibrium to be 10 newton in the opposite direction. You get it now? You get it now? Right, now I want to talk about another principle called the Lami's principle. The Lami's principle states that Lami's principle. It states that if three forces are in equilibrium, if three forces acting at a point, that's very important. So they must be concurrent forces, are in equilibrium. Then each force is proportional to the angle between the other two forces, or the sine of the angle between the other two forces. So it's better to see this in the diagram. So it's like another way to solve problems like this triangle law problem that we have down here. So it says that if I have three forces in equilibrium like that, okay, and I have this as angle alpha, beta, and gamma, so this is A, B, and C, then the force A over sine alpha, where alpha is the angle between the other two forces, equals the force B over sine beta. If I'm considering B, beta is the angle between the other two forces, and it's equal to the force C over sine gamma. So this is Lami's principle. So we can use that to solve this problem. So after simplifying this problem to look like this, okay, which is the picture problem, T1, T2, and the weight. So all I need to find is this angle, and this angle, and this angle. So this will be 60 plus 90 totally for this angle, and that's going to give me 150 degrees, and this angle will be 70 plus 90. That'll give me 160 degrees. Okay, and this angle is going to give me, So if I have a 160, 150, that's 310 from 360. So this is going to be 50 degrees. Okay. So altogether, all I have is this. So using Lami's principle here, it means T1 over sine 150 degrees equals T2 over sine 160 degrees equals the weight 20 Newton over sine 50 degrees. So you can use this to solve. So do this first part, T2 over sine 160 to get T2. Then you can use this to solve this or equate this to the 20 over sine 50 to get that. So you could just say T1 over sine 150 degrees is 20 over sine 50 degrees. You solve for T1 and you say T2 over sine 160 degrees is also 20 over sine 50 degrees. You solve for T2 from there. So this is using Lami's principle to solve. So there are lots of techniques you can use for this. So now I can introduce you to the moment, the law of moments, and we'll just solve a few examples and then we're done. Alright, so what do we mean by the moment of a force? So the moment of a force acting at a point, so if I have a point, I have a force acting at some distance from that point, okay? So I have a force F acting here at a distance A from this point I call O. So we say the moment, or also known as the torque, okay? The moment or torque of the force F. So remember, this is equilibrium under the action of coplanar forces. And we say coplanar forces are forces that are parallel to the same plane. Okay? So this force is parallel to that plane, this plane of the board. Okay? And these forces, we're going to see they are distributed along the body. That's why we're going to introduce the different methodology of solving this kind of problems. Okay? So the moment or torque of the force F about point O is the measure of the turning effect F has about O, or the amount of rotation that F can give to the point O, okay, if let to rotate, okay. So it is given mathematically that the moment of force about O, let me call it M, okay, or you say torque T about O, okay, is equals the force multiplied by the perpendicular distance. That's very important, the perpendicular distance to the object, A. So F times A is giving us the moment of force, or the torque, okay? Okay, it's giving us the torque. In vector notation, okay? In vector notation, we are going to replace this with, say, torque equals R cross F, where this is multiplication, this is times multiplication, and this is the cross product. Okay, the cross product is magnitude of R, magnitude of F, sine theta. Okay, like that. So now we will leave this this vector notation first. We'll solve the simple one and then we'll explain how this works. Okay, it's quite easy. Okay, so we'll just multiply. So what happens is, if I have what I call the pivot here, okay, which is like a turning point. So I have a boy sitting here and another girl also sitting here. So the distance from this boy to this girl, the pivot is A. The distance here to the boy is B. And let's say the weight of this girl is, say 500 newtons, and the weight of the boy is, say, 800 newtons. So I can ask you to find the moment of this boy about the pivot, the turning point, okay? Okay? Or I say, find the moment of this girl about the pivot, okay? So this turning point, that's what, it's very important, okay? We take a moment about the turning point, which is the pivot, okay? Now, if I'm taking the moment about this point, it's going to be the force times the perpendicular distance. So for the boy, it's going to be 800 times B. And for the girl, it's going to be 500 times A. Okay, now I told you when we have such equilibrium, when they are sitting, say they're in equilibrium, it's static, nobody is overpowering the other, like nobody's weight is going over, so it's just flat. So we say we have equilibrium under the action of coplanar forces now. So what is the math here? What is the physics here? Simple. Remember the first law of equilibrium? The first law of equilibrium that states that the summation of forces in the x and the y and the z must be 0. Upward forces, downward forces balance, sideways forces, left, right-handed forces balance. So now we introduce the second law of equilibrium. And this first law is called law of forces. And the second law is called law of moments. So law of moments says that the total torque or total moment about any point, any given pivot, okay, must equal 0. Okay? The moment about any pivot or any point at all, doesn't have to be a pivot, must be 0. Okay, this has different meanings because we can have the moment here, the rotation this guy will produce is counterclockwise, and the rotation the girl will produce is clockwise. So we have two kinds of moments: clockwise moments, counterclockwise moments. So in physics, if you take clockwise moment to be positive, you take counterclockwise moment to be negative. So if this system is in equilibrium, we are saying that the clockwise moment, if we take clockwise as positive, 500 times A, and counterclockwise moment as negative, minus 800 times B, must be 0. This is what we mean by the net torque must be 0. The net moment must be 0 if the system is in equilibrium. So in other words, in another way for saying the second law of equilibrium, the law of moment, I'm going to use the simple word that say clockwise, just say clockwise moment or torque must equals counterclockwise moment. So your total clockwise moment, sum up together, must be equals your total counterclockwise moment. This is the easiest way. Instead of dealing with the positive and negative sign, solve for all the clockwise moments, solve for the counterclockwise moments, and equate them. So I'm going to take an example to explain this so you get the picture more clearly. Okay. So simple example, let's say the boy and the girl again in the pivot like this. Now I have 5 meters and here I have 7 meters, okay, from here, okay. Let's say this thing has no weight. So the only weight we have here is, say, 800 Newton and the 500 Newton. Good. And I say, calculate the clockwise moment here. So this one is going counterclockwise to the pivot. This one is going clockwise to the pivot. So I'm taking moment about the pivot I call A. So I say taking moment about A, okay? Taking moment about A, clockwise moment, total clockwise moment. So the same thing as torque, clockwise torque, is just 500 times 7, 3500. The unit is Newton meters, force times distance. I forgot to mention that the unit of torque or moment is Newton meters. So what about total counterclockwise? Counterclockwise moment or torque would be this guy, 800 times 5. 4,000 Newton meters. Okay? Good. So the clockwise moment is that, the counterclockwise moment is that. Okay? So in this case, you can see that the clockwise moment and the counterclockwise moment are not the same. They are not the same. So it means this system will not be in equilibrium. So for a system to be in equilibrium, they are supposed to be the same. So I'll give an example like that. So let's now say we want a system to be in equilibrium. So let's say this guy is 5 meters. So what distance will this guy be, x, for this system to be in equilibrium? So for this system to be in equilibrium, clockwise moment and counterclockwise moment now have to be the same. So I will say 800 times 5 must be equals 500 times x. So what will be x? 800 times 5 divided by 500. Okay? That will be 8 meters. So x has to be 8 meters. So for this girl to balance this guy, she has to move an extra 1 meter instead of 7, 8 meters. So they will balance each other. Okay? That's how moment works. Now we can have more than one moment. Also, we'll have 2 people sitting here and 1 person sitting there. So we'll have 2 clockwise moments coming from those 2 guys. We sum them up. They must balance the counterclockwise moment coming from this guy for that thing to be in equilibrium. Okay? So what I'm saying now is this, another example. So I have, so let's say this, it has a weight, okay? And okay, let's say it's acting at the center. So when your pivot is at the center of the weight cannot have a moment about that point. So the weight is negligible. So here, let's say we have the same 500 newtons at some distance, say x. And now we have 2 people here. This guy is 2 meters from here and it has 600 newtons, and this guy is 3 meters from this guy, okay? And it has, say, 700 newtons. And I say, at what distance will this guy be? Or in fact, at what distance will this guy be to balance these other guys? So we take moment about the pivot. This is clockwise. So I have 2 clockwise now. So my total clockwise is 600 times the distance from the pivot, 2, plus another clockwise, 700, times the distance from the pivot, 3 plus 2, 5, must be equals this counterclockwise, 500 times x. From there, I can now get x. Okay? So 600 times 2, 1200, 700 times 5, 3500, must be equals 500x. So what is x? Is 1200 plus 3500, which is 4700, divided by 500. So it's 47 divided by 5. Okay? So it will be 9.4 meters. So sometimes they will give you the distance and ask what weight will be here at this distance to balance these other 2 guys. So take the clockwise moment, equate it to the counterclockwise moment, and then you can easily get that. So long as you have equilibrium under the action of these coplanar forces. Now let's go to some complicated examples, okay? I'm just going to give 2 more complicated examples. So we see how to combine the first law of equilibrium, the second law of equilibrium, the law of forces and the law of moment. So let's say we have a uniform bar and we have the pivot at the end, like this. So the weight of this bar acts at the center because it's uniform. And let's say it's 15 newtons. And then we have somebody here of weight, say 10 newtons, at some distance, say 20 centimeters from here, from this end. And this is 10 centimeters from this end. So we have another guy 15 centimeters from this end. And that guy is sitting here and say he's 30 newtons. Good. So the question is, we are asked to find the reaction at this pivot. Okay? Okay, we are looking for the reaction at this pivot. Because the weight of these guys acting at this pivot, there will be a reaction, and the reaction will be upward. So I call this reaction RA from the point A, and this reaction RB from the point B. So what are these reactions? So now we're going to take moment about one pivot. So if we take moment about A, say taking moment about A. So what is the distance? Okay? The reaction of A about A will have no moment because there's no perpendicular distance at all. So it's 0. So we are going to take this will be clockwise, this will be clockwise, and this will be clockwise. But this reaction coming here will be counterclockwise. So we'll have 3 clockwise moments and 1 counterclockwise moment. So that reaction will be a force that is going as a moment. So taking moment about A, all the clockwise moments are 10 times 20, you can work in centimeters and newtons so long as you work on the same side too. Okay, 10 times 20 plus 50 times 10 plus 20, so it's 50 times 30 because we are taking the distance from here to the pivot. Plus 30 times 30 plus 15, 45. 30 times 45. These are the total clockwise. Equals the counterclockwise, RB times the distance between here and here. This is the center. So this is 30. So this will be 60 centimeters totally. So this will also supposed to be 15 centimeters. Don't mind my scale diagram, it's not that much. But so since the weight is at the center, 15 inches, 30, here will be 30, so 60 centimeters. So RB will be 60 from where we're taking the moment. So always note you are taking distance of every force towards the moment point. Okay? So from here we can get RB. So this is 200 plus 1500 plus 1350, because this is 45 times 2, 90 plus 45, 135, okay, equals 60 RB. So you sum all of this together, this is 1700, okay, plus 1350, okay, this will give us 3050, okay, so 3050 equals 60 RB. So from here we get RB to be 3050 divided by 60. 305 divided by 6. Okay? That will give us about 50 something. Okay? 50 something. About 50 point something. 50.9 or so. Now, this is the reaction at B. Now, what is the reaction at A? A way to get reaction at A is now to take moment about B. And now these guys will now become counterclockwise, coming to B, and this guy will be clockwise. But that will be too long. This is where you know how to use the simple way. The first law of equilibrium can now solve this. Because according to the first law of equilibrium, the total upward forces, RA plus RB, must be equal to total downward forces, 30 plus 50 plus 10. And you're done. So RA plus RB, we already got RB to be 50. So RA plus 50 point something equals 30 plus 50 plus 10, which is 90. So what is RA? Is 90 minus 50. That'll give us 40 newtons. And you're done. So you don't need to take moment about RB to get RA. But if you take moment about RB, you still get the same answer, but it's a long procedure. It's a long procedure. Okay? So I want to end this by teaching us how to solve the ladder problem. Okay? We are going to do another class with just solving problems on equilibrium, and then we'll go to more difficult, we'll see more difficult problems on this, okay? This class is just explaining the basic concepts, okay? So now, we have a ladder leaning on a wall, like this, so we'll have a wall like this. So this is our wall. I will have a ladder like that. So this ladder, I'm trying to make it look like as real as possible, okay? So we'll have this ladder like this, okay? Something like that, okay? So this ladder is inclined at an angle, say 60 degrees. And the weight of the ladder says at the middle, at a distance 0.5 the length of the ladder. And the weight is, say, 200 newtons. And we'll have somebody sitting at a distance here. Somebody is on top of the ladder at a distance here, 0.2 L from this side, okay, the length of the ladder is L, okay? Good, and this person has a weight of, say, 500 newtons. So the question is, what is the frictional force that will hold the ladder if the ladder is not to slip? And what is the equation of friction? So we are finding the frictional force here, F, friction, and also the coefficient of friction, which is frictional force over normal force at the base of the ladder. So these are the two questions, this and that. So to solve this problem, What we're going to do is we're going to draw a free body diagram. So we assume that the wall is smooth, so the only force coming from the wall is like this. Okay? And then we should not forget, this will explain a lot of things for us. So we have the weight of the ladder in the middle, which is 200 Newton. And this guy coming here. So the distance from here is 0.5 L. And the distance from here is 0.8 L. Because we have from here. Because we have 0.2 left from here. So this is the wall. And this is the floor. Okay? So the only force acting on the wall is what I call the normal reaction from the wall, N2. We have the normal reaction from the floor, N1. And we have our friction, Fr. Good. And this is 60 degrees. Now, first of all, I'm going to do the total, the law of the first law of equilibrium, law of forces. N2 is coming this way, friction. So N2 must be equal to friction first. Okay? And then what else? N1 must balance, N1 is going up, it must balance 200 plus this guy's weight, 500. So 200 plus 500, 700 Newton must be N1. So that's my normal force coming from the bottom. Okay? And N2 must balance my friction. Now, how can I get N2? Once I get N2, I have gotten my friction. And I already know N1. And I'm looking for mu, which is friction over N1. So I know N1, all I need to find is N2. So how do I get N2? I take moment about here. So if I take moment about here, this will be clockwise, this will be clockwise, and N2 will be counterclockwise. But now we have to mind the angle. This is 60, this is 30 degrees, this is 30 degrees. Now to make this triangle like that, I have to get the vertical component of these forces because my moment has to be perpendicular to the surface. I have to get the vertical component of these forces to multiply by the perpendicular distance. The same, I have to make this force perpendicular. This N2 force here must also be perpendicular force. So this is 60, here is also 60. Now, my counterclockwise moment is N2 sine 60 degrees, which is the component perpendicular to this ladder, multiplied by the distance L, the total distance of the ladder, must be equal to the 2 clockwise, 200 sine 30 degrees, because I have taken the vertical component perpendicular to the ladder, multiplied by 0.5 L, plus the other clockwise moment, 500 sine 30 degrees, multiplied by 0.8 L. Now the L's we cancel from both sides. So this will give me 200 sine 30, that's 100 times 0.5, that's 50 plus, okay? So this is N2 equals 50 plus 500 sine 30 is 250 times 0.8, so it's 250 times 0.8 plus 50, then divided by sine 60, 0.866. So this is what you get for N2. So when I get N2, I put it as my frictional force, okay? And then I can now divide it by what I just got for my normal force, okay? So this is how you solve the ladder problem. So the bottom line here is, if I have a force perpendicular 10 Newton at a distance, say 5 meters from point A, and so what is the moment about A? It's just 10 times 5. But if the 10 Newton is inclined at some angle, say 30 degrees, and I want to find the moment of 10 Newton about 5 meters from point A, I'll take the vertical component perpendicular to that. So it's going to be 10 sine 30. That will multiply that distance to get the moment about that point. The force has to be perpendicular always for you to get your moment. So we're going to do more examples on this in our next class, and then we'll see how we can. So we'll take a lot of examples and practice this a lot more for us to understand how this works. Okay, thank you for today.